Hello, AP Chemistry. Let's do a little introduction on our new chapter on kinetics. Kinetics is really talking about the rates of reactions, how fast reactions occur. So that's what we're going to be doing in chapter 13. Later, we're going to be doing chapter 18, which is similar but different, called thermodynamics, where we're going to be calculating delta G, where you're really trying to figure out, does a reaction occur? And if so, is it favorable to occur and how much? So we're not going to concern ourselves with that at this point. We're only going to be concerning with kinetics, which has to do with how fast the reactions occur. So today we just really need to know what rates of reactions are and how to calculate them. So the first part, it just gives us the definition. Rate of the reaction is the change in the concentration of a reactant or a product with time, compared to time. So you can measure how fast the rate of a reactant, say A, is our reactant, decreases. So the disappearance of reactant A would give you a rate of the reaction. Or we could measure the rate of disappearance, the rate of appearance of B, which would be your product, right? So either way, you can get a rate of the reaction. So you can do one or the other. So the rate of disappearance, it's always the change in concentration over time. We do need to put in a little negative there because the concentration is going to decrease, and so this top difference in concentration is going to come out negative, and we want the rates to always come out positive. So these values of rates are always going to be positive values. The rate can't be a negative. So always make rates positive. If you have a rate of appearance, this change in concentration is going to come out positive, and so the whole thing is going to come out positive without a negative out in front. So let's do a quick calculation. So what I mean by that is if I give you this graph here, where you have this data over here on the graph, using the data from the graph, calculate the rate of disappearance of A when going from time 10 seconds to 40. So we're going to go from time 10 seconds to time 40. We're looking at A only, so I'm going to read up our concentration of A to start is 30, and then at time 40, we don't want to go up to B. Time 40, we're going to end here. So we're going from here to there. So what we're going to do is the rate, and remember, this is the disappearance of A, right, is going to be equal to the negative of the change in concentration of A. So it's always final minus initial. So the final concentration, we're just doing numbers of molecules. You could do it in molarity, would be 10. So we're going to have 10 molecules, right? It could be in molarity, minus the initial was 30 molecules there, divided by the change in time, 40 seconds minus 10 seconds, right? So if you simplify that, obviously, we're going to keep that negative. So negative 20 molecules are going to be lost, right, over that time, over our 20 seconds, 30 seconds that are going by. When you divide that out, that is going to give us a positive, oh, see, and I already did it wrong. Let me fix. 10 minus 30 gives us negative 20 molecules. And so with our negative, now it's going to come out positive, 0.67. In this case, we're measuring it in molecules per second. Normally, you're going to measure in molarity per second, right? So let's just write that in. Often in molarity per second. Okay, so anyway, the rate of disappearance should still come out positive, even though the concentrations are going down. You're going to put in this negative to make it come out positive. So now let's do the opposite, and let's do the rate of appearance of B. So we're going to use the same graph here. Now we're going to do the rate of appearance of B, right? It's a product, and so it's going to appear. We're going to plug in the same idea. Now for B, let me get a different color here. In B, we're going to be going from here to there. So you're gaining molecules, right? So when we do the rate of appearance, we just need the change in concentration. So final minus initial. Final concentration is 30 molecules minus the initial 10 molecules divided by our change in time, 40 seconds minus 10 seconds. We're doing the same time period from 10 to 40. We have no negative here, so when you subtract 30 minus 10, obviously we get 10 molecules divided by our 30 seconds, which comes out as our same 0.67 molecules per second. So in this case, the rate of disappearance of A is exactly the same as a rate of appearance of B. And it doesn't always have to happen, but it does in this case, because for every 1 mole of A that disappears, 1 mole of B appears, right? Or 1 molecule of A to 1 molecule of B. So these are the same because you're having the same mole ratio, right? So let's just write that in. Same rates because 1 to 1 mole ratio. Later on the back, we'll do calculations where the mole ratio isn't 1 to 1, but if the coefficients are 1 to 1, the rate of the one is the same as the rate of the other. Okay, hopefully that's pretty clear. Just so you know, if you don't want to worry about this negative out in front, you can always just take the difference of your concentrations and just make it positive so that your rate always comes out positive. That's fine with me. In some ways is a little bit easier, so you don't have to worry about the negatives. Okay, let's move on to our next example. This one is more of like a real situation here. We're imagining we're doing this reaction, Br2. This is actually formic acid going to Br minus with H plus and CO2. And the reason this reaction can easily be monitored is because Br2 has this red color, right? And over time, once it reacts and the Br2 is gone, it's going to turn colorless. Your Br minus is colorless. And so when you lose your Br2, the solution will go from red to orange to yellow and then eventually to colorless once all the Br2 is gone. So because you have this great color change now, we can use a spectrometer to measure that change in absorbance. So what they're going to do here, they're going to use 393 nanometer light to send through the spectrometer to detect how much absorbance of that 393 nanometers of light. The reason it's working is because for Br2, this is the absorption of the Br2 solution, right? Around 393, we have really good high absorbance, right? We have high absorbance here of the 393 nanometer light. That is a relatively blue color, high absorbance of blue light. And so that's why the solution is looking pretty red. It has very low absorbance in the red spectrum. So there you go. So we're going to, when it looks red, it's going to have really high absorbance of blue. So that's why we're going to use blue light here. And see how much absorbance we have. So the more it's red, the higher the absorbance of that blue light. So you can get, over time, you measure the absorbance and you change your absorbance. So then this is high concentration of Br2, right? So when you have high absorbance of that blue light, we have high concentration of Br2. It's a very red solution. So they just get all the concentrations. They change from absorbance, right? So use absorbance, convert from absorbance, right? Use Beer's law, and they're going to then get their concentrations. So when you have high concentration of Br2, it's because it's a really red solution. And as you go and the reaction proceeds, it eventually will turn colorless and the concentration of Br2 is decreasing. So let's look at the rates over here. We have a plot over here of how those concentrations are changing. So this is the concentration of Br2 in molarity over time. And we see obviously the concentration of Br2 is going down. The interesting thing is that the rates of it going down is actually changing over time, right? So what you want to be able to do is you want to look at, if you look at this point here, if you take the slope of this line right at that point, the tangent right at that point there, you can get the average, you know, what was the concentration here, what was the concentration here, and we can get an average rate over time, average rate from in that time period, right? And what you see is if you get it instantaneously, this, I'm not drawing very well here, but this, if you draw the slope, the tangent right at this point, right, that's this line right here, that slope is steeper than here. If you take the tangent at this point here, do you see you have a flatter slope here and you have a steeper slope here? So when you have a steeper slope, that means your rate is faster, and when you have a flatter slope, that means you have a slower rate. So as the reaction goes, the concentration of Br2 decreases, and that slows down the rate. So we can see that on the graph. So as the concentrations decrease, the rate of the reaction is actually also decreasing. So the rate of the reaction often changes as a reaction progresses because the concentrations of reactants change, right? So that changes the rate of the reaction. So let's calculate. We're going to get the average rate of disappearance of Br2 over the time interval from 50 seconds to 100 seconds in this case, using this data. So we're doing the same thing we did before. We have concentrations at different intervals. We are going to go from 50 seconds to 100 seconds. So it's, you know, here's 50 seconds on your graph. So we're going from 50 to 100 is what we're doing there. So on your data chart, 50 to 100, right? We're just going to go from here to here, and the concentrations have obviously changed from there to there. So these are going to be our concentrations that we're going to use and our time interval. So the rate, this case we're going to do the disappearance of Br2, because remember Br2 is a reactant, and so that's going to be disappearing. So the rate of disappearance of Br2, we need to officially put in that negative, because again, the concentrations are going to decrease. So we're going to, the time final, the concentration is 0.00846 molar. And then we're going to, so final minus initial, 0.0101 molar, over final minus initial, 100 seconds minus 50 seconds. When you subtract this out, you'll still have your negative here at the top. It'll come out as negative 0.00154 molar over, obviously, our 50 seconds on the bottom. When you calculate that out, you'll get a positive number, 3.28 times 10 to the minus 5, and the units are molarity per second, which is a rate. So there you go. So it came out positive. That is the rate of disappearance of your Br2. So that would be great. Now, what if they asked you for the average rate of appearance of CO2? So we're getting the average. We're just going to go over the same time interval. Now, we don't really even have to make a calculation, because look at the mole ratios. Let me go back up to the top. We need to look at our reaction. For every 1 mole of Br2, we are going to get 1 mole of CO2. So it's a 1-to-1 mole ratio. So when you lose 1 mole of Br2, you're going to gain 1 mole of CO2. So even without the data, we know the answer because it's a 1-to-1 mole ratio. So we're going to say rate of disappearance of Br2 is equal to the rate of appearance of CO2 because 1-to-1 mole ratio. So the rate for the CO2 is going to be the same exact thing, 3.28 times 10 to the minus 5 molarity per second. So you just be aware of that. If it's a 1-to-1 mole ratio, they're going to be the exact same rate, so you don't have to calculate. Okay, now all of these examples we had 1-to-1 mole ratio. So on the back now, we need to look at the situation where it's not a 1-to-1 mole ratio. It's really not much harder. Let's see if we can do this. So in this example, we're going to have 2 moles of the N2O5 forms 4 moles of NO2 and 1 mole of O2. So because we have those coefficients, we have different stoichiometry. So here I have another graph, and this is what it kind of looks like. So the rate of N2O5 is a reactant. It decreases, right? And you'll notice for NO2 is a product, it's increasing. I don't know if you can tell that the NO2 is increasing faster than the N2O5 is decreasing, right? And that's because it's for every 2 moles you lose here, you gain 4 moles of NO2. So it's increasing at a faster rate, and you can see that in the curve. The O2 is actually increasing at a slower rate because it's only got a coefficient of 1 there. So let's make a calculation. So in this question, from the graph, it can be seen that the concentration of N2O5 decreases by 0.0019 molar in 100 seconds. We're going from time 300 to time 400. So that is right here. They're looking at this time period between 300 and 400, okay? And we're looking at N2O5. So we're going from here to here. And that time is 100 seconds, and they're saying that that decrease going down from here to here is negative 0.0019 molar. So that's what it's telling you on the graph. So we don't have to calculate. It's kind of already been calculated for us. So we're doing the rate, and this is going to be for the disappearance of N2O5 is going to equal to, it's a disappearance, so we need that negative, and the concentration is being lost, so it's negative 0.0019 molar, right? The change in the concentration over the change in time, which is 100 seconds. So that rate is going to come out as a positive 1.9 times 10 to the minus 5 molarity per second. So that is all we have to do to get the rate of disappearance of the N2O5. Again, the value should come out positive even though it's a rate of disappearance, right? Okay, now let's get the other ones. We already know the N2O5, so now we're just going to use our stoichiometry to get the other ones. What must be the rate of appearance of NO2 over the same time period, right? Same time period. 2 moles gives 4 moles. The rate has got to increase twice as fast. So all we're going to do is we're going to take the rate of the N2O5, 1.9 times 10 to the minus 5 molarity per second, and we are going to multiply by 2. And so you're going to get 3.8 times 10 to the minus 5 molarity per second. And so that's going to be our rate for NO2. Okay, and it's just twice as much, right? Rate of NO2 is twice as fast because 2 moles of N2O5 forms 4 moles of NO2. So all we had to do was multiply by 2. That is the key, right? All right, so now let's do O2. Easy enough. Let's use our rate of the N2O5 again. We start with our 1.9 times 10 to the minus 5 molarity per second. In this case, we're going from 2 moles of the N2O5 goes to 1 mole of the O2. So 2 moles to 1 mole, we actually need to cut it in half. So I'm going to multiply by a half, and we're going to get 0.95 times 10 to the minus 5 molarity per second. But let's change that into scientific notation. 9.6 times 10 to the minus 6 molarity per second. So that would be our answer there. That is equal to the rate of appearance of O2, right? So again, let's just write the rate of O2 is half the rate of the N2O5 because 2 moles of N2O5 forms 1 mole of O2, just from the balanced equation. See how easy that is? Once you get one rate, you can then just compare using stoichiometry to get the rates of the other one. Okay? Always the rates are going to come out positive. That is really all I need to tell you. You should be able to do the homework. I just want to point out this little bottom caveat I put down here, just saying that in the book they explain this stoichiometry situation a little bit differently, and they use this formula. It comes to the same thing as what we have just explained using stoichiometry. It just looks really confusing, and I think it's unnecessarily confusing. So there's no reason to use this formula. If you're reading in the book, just totally don't pay any attention to that formula and just use stoichiometry, your coefficients in your balanced equation, and you're going to be able to figure out your rates. That's it. Have a good day.